Welcome everyone. I got it a little bit from Aki where you are in this class. I assume you kind of know what multibody is. Probably already tried to model some things as multibody systems, solve them. But this is just the beginning, right? If you want to solve real world problems, you certainly need well, in certain applications to have the machinery for multibody dynamics and be able to solve this, but very rarely do you only need to solve a pure multibody system problem, right? Aki already mentioned mechatronics and interaction of these mechanical systems with the environment. Think of a vehicle and interaction with the terrain. So you need to bring in a lot more than just multibody. So Chrono is a open source piece of software set of packages that allow you to do all sorts of simulation of this kind. So and this is what I want to talk about today. Now, this is a very long outline. As I said, I have probably like 90 some slides. I am not going to go through all of them or touch upon them, but skip some. I'll make these slides available so that you have the full set if you want to look through the ones that we don't get to go. But I'll just tell you a little bit about what Project Chrono is, talk a bit about the capabilities of Chrono, and then we'll use ground vehicle modeling as our prototypical type of problems that we want to solve. Chrono can do a lot more than that and is used in a lot more different applications, but we just use that one to illustrate what you can do with such software. All right, so before we start, let's try to set up some context and see what such simulation software can get you. And for that, I want to use this slide about the modeling process. This is people from Hertz started thinking about what it means to model something. And this is a schematic that I picked from Kaiser and Stender 10 years or so ago. And I extended it a little bit to fit better what we want. So what we're trying to do is to understand a real phenomenon. You can see my cursor, right? Yeah, okay. And so we want to understand the real phenomenon, and by looking at some meaningful results for that thing. And well, of course, you can do experimental testing, but that is expensive. It can be dangerous. It's limiting in terms of how many actual physical experiments you can do and things like that. So we like to use simulation for that. Now, in order to be able to simulate and understand this real phenomena through simulation, you need to go through some steps and close the loop, come back to reality at some point. So the first thing that you have to do is to create a model of your phenomenon, but still in the real world. So just a simplification of the system that you try to model, to understand, that captures the essentials of that phenomenon. And this, I mean, there are some words here that sound a little bit made up, because some of them are, but you need to understand what the real phenomenon is, simplify it, and then specify what it is that you need to know about the real phenomenon in order to understand it. And just to exemplify this, let's say that the real phenomenon is a grandfather clock, right? You know this old style clocks that have a big pendulum to regularize the motion of the clock. So that's our real phenomenon. And say we want to see, find the period or something like that. Well, obviously that has lots of parts that are completely irrelevant to the task that we have at hand. So first, we need to simplify the problem and say, you know what, I'm going to model this as a simple pendulum. right? So I'm still in the real world, and I replaced the complex phenomenon that I want to study with a simpler physical model, a single pendulum. Well, at that point, we still didn't make much advance, because if I were to understand a real single pendulum, I would still need to do experiments. So I don't want to go that route. Instead, we create now a mathematical model, and we move from the real world to mathematics. And for this one, now you need to know physics, you need to know mathematics, and capture some equations that idealize the behavior of that real world simplified model. So you have a mathematical model. Now, if this mathematical model is simple enough and you can solve this by hand, say, then you do some mathematical work, whatever that means, and you get a mathematical result. This one, then you convert back into the real world in physics, and you get some real world results. And once you get these, you can see how close this match experimental data, for example. That's a validation step. Or you can try to compare between these two, the results that you got by going through this loop with some experimental results that you would do in a lab, say on a single pendulum, with the specification that you decided on here, so that this single pendulum represents a idealization of your grandfather clock. Now, this is what Kaiser and Stender, for example, did, because they assume that this can be done. The problem is that for complex real phenomena, you end up with complex mathematical models. And you already know that multi-body dynamics already takes you to DAEs and things like that, which are very unlikely to be solvable by hand. So then what we do here, we extend this loop and say, well, we're not going to solve the mathematical model by hand. Instead, we transfer from mathematics to, I call it technology here. Effectively, we create a computer model that is a representation of that mathematical model. And this is done by programming, right? Implementation. And of course, some numerical analysis also, it's in here. And now what you do with a computer model, you simulate that model. So a simulation means exercising a computer model, right? So modeling takes place here and a little bit here in terms of numerical methods. Simulation is this step here. Now you get the computer results. This is time series, discrete data, whatever you get from your computer program. You bring this back into mathematical results through data analysis, and then you're back in the old loop, right? So this is the modeling process that we typically work with when we talk about complex multiphysics problems that we solve through computers. Now, something like Chrono, which I'll describe in the next couple of slides, will help you with this part. So Chrono is not going to help you model, right? So all these things you have to do yourself. Once you decided on a real world model and say, well, it's a simple pendulum, or it's a connection of bodies that represent a vehicle, well, then Chrono can help you put together that mathematical model, and then it has implemented the numerical methods to solve whatever equations you end up here, whether they're ODEs, DAEs, PDEs, and so on. And then, it brings you back to the mathematical results. And then again, you're on your own. You have to interpret whatever mathematical results you get from, with your engineering intuition and the knowledge, and bring everything back in the real world. Okay, so we are going to stay within this red circle here. Engineering and simulation, it's more than that. It also includes this part here, which, there's really no software to, well, nowadays people into AI and things like this claim that they can also help you with this part, but the jury is still out there. All right, so what is Project Chrono? Project Chrono is a set of libraries for multiphysics simulation. It's developed together by us at the University of Wisconsin-Madison in the United States with our colleagues from Università di Parma in Italy. It's been around for quite a while, probably 30 years, almost as long as, as I've been in this field. What's important about it, it's open source, and it's also released under very permissive license, meaning that this BSD3 license makes it possible for a company to just take this software and do whatever they want with it, sell it if they want, repackage it, extend it, without having to open up their own editions and things like that. We took this decision because this allowed us to make Chrono as pervasive as possible and as widely adopted as possible. Now, at its core, Chrono provides support for multi-body dynamics and what we call many-body dynamics. This is just, a wordplay, if you want. This really means granular dynamics. So I'll show you examples of simulations where we deal with millions of bodies that all interact with each other through frictional contact. That's granular dynamics. We call it many-body dynamics. We have support for nonlinear finite element analysis, and there's going to be a slide on this as well. Not your regular, linear finite element analysis, because we're interested in large displacement, large deformation. You'll see the kind of examples that we're after. And also fluid-solid interaction problems. So these are problems in which solids, whether rigid or flexible solids, interact with some sort of fluid, which can be water. We don't do aerodynamics, but we do incompressible fluids, water, and we also use this to piggyback on it for deformable soil, and I'll show you how that goes. The code is a C++ code, but we have wrappers for Python and C#. Python mostly because this is the preferred language for machine learning, right? There's a lot of machine learning tools that are in Python, and it's nice to be able to have the simulation software also be easily callable from Python. And C# because we have a Unity interface to Chrono, and I'll show you a couple of video or two about that as well. Again, what is important, the Chrono libraries are middleware libraries, which means that unlike, some other simulation software, commercial simulation softwares, where all you get is an executable and you just run that one, you model everything, you don't see the code, you don't work with the code. With Chrono, that's not the case. So there is really no user interface, so to speak. You have to write your own code and link to the Chrono libraries and leverage the capabilities of Chrono by making calls in the different libraries of Chrono. So Chrono is organized in a sequence of what we call modules. In that, these are add-ons. So you decide what kind of problem you need to work with, and you only enable, when you build Chrono, you only enable the modules that you're interested in. It doesn't make sense to enable a zillion different things. Now, all of these are on the same level. They are modules, but they all serve different purposes. This what is it, 5 here, are modules in Chrono that allow you to model different physics, right? So the core module, which is always there, always enabled, this is the multi-body dynamics and finite element, right? Then if you enable the FSI module, you also get fluid-solid interaction capabilities. The model module allows you to do model analysis. Peridynamics, this is probably the newest module in Chrono, developed in Parma. This is a non-smooth formulation for peridynamics. Peridynamics is this approach of modeling fracture and deformable materials, right, with particles, right? That that interact at a finite horizon. So we had all the machinery needed to add peridynamics, and the guys in Parma did this recently. And Sensor is a module that provides physics-based models of sensors. These are used in autonomy, for example. So we have models of cameras, LiDARs, radars, IMUs, GPS, and so on. Okay? So all these represent different physics, right? And if you go back to the modeling loop that we had there, they all result in different mathematical models, right? So the multi-body dynamics will give you index 3 DAEs. The finite element will give you a set of PDEs that are discretized with finite elements. FSI, you need to be able to solve the fluid phase. And so you have some PDEs like incompressible Navier-Stokes or some continuum solids for deformable soil. Model, well, yeah. So here you do an eigenanalysis, right? It's a different type of mathematical thing. Peridynamics allows you to solve these things with for fracture, for example, of material. I don't think I have any slides on this one in this presentation, but the underlying equations are still DAEs with non-smooth contact, which we also do there. And the models for sensors, well, that depends on the sensor, right? So there are all sorts of different models for cameras, for LiDARs, and things like that. They very often they can be just finite state machines, not that often continuous models that would be modeled by some differential equations. Then we have some facilities to quickly model things in chrono, because if you think of it, well, modeling a single pendulum, not a big deal. You know, it's one body, one joint, you're done. But when you have to model something like say a track vehicle with, you know, zillions of track shoes and engines and suspension parts and all that, it's difficult to do it from scratch, right? Body by body, joint by joint, and force, you know, spring by spring, and so on. So we have these modules like the vehicle module that uses a so-called template-based approach to modeling ground vehicles, wheeled and track vehicles. And then we provide a set of parsers that are split into two. They are either importers from third-party formats. So URDF, which is the Unified Robot Definition format, it's quite common in robotics to have a full description of a robot in this URDF thing. We can just take a file like this, which is an XML file, and create a chrono model that represents that robot. ADM is for those of you familiar with Adams. We can take, well, this is only partially implemented because it was more of proof of concept. We take one of their specification files, again, a text file, and create a chrono model based on that. OpenSim, for those of you working in biomechanics, OpenSim is a software for simulating biomechanical systems, which under the hood have also a multi-body system for the skeleton. We can take their input file and create a chrono model. And more recently, I started working on this thing, which is a YAML-based parser for specifying chrono models. So once this one will be completed, you'll be able to specify any, well, almost any chrono model and simulation only in YAML, which is, again, a text-based format. Then we have modules that target different hardware. So for certain of the problems that I said chrono is suitable for, different hardware is more suitable. So when you want to do granular dynamics with millions of interacting bodies, it's very expensive to do it on the CPU, but the GPUs are really good at doing that. So we have a module that does granular dynamics on the GPU, so DEM. Then we have a module multi-core that parallelizes vehicle dynamics and multi-body dynamics in general, not finite elements, on the CPU, but taking advantage of multiple cores on modern processors. And then we have a module that allows you to distribute simulations across a network of computers. And this is when you have relatively loose coupled agents, we call them. Think of if you want to model traffic in an intersection and you have 20 different vehicles, right? Assuming that they don't collide with each other, so in a normal scenario, you can have all of them simulated on different nodes, but they have to share the same environment. So if you're off-road, when one deforms the terrain, the other one needs to see the ruts and drive over the ruts and things like this. So this is what Synchrono gives you. Then we're going now lower level. MKL and MUMS are just interfaces to different external solvers, in particular for direct sparse linear solvers. These are needed for finite element, for example. Then we have support for runtime visualization and post-processing. And you'll see all the example simulations that I'll show you are done either with Irrlic. VHD is the newer one and more capable one. We'll soon probably get rid of Irrlic. And for post-processing, if you want to get prettier pictures and movies, then we have the support to export to POV-Ray or to export to Blender and create nicer animations and things like that. And finally, almost finally, we have modules that allow you to interoperate with other software. For example, Cascade allows you to import Open Cascade models. FMI, it's a relatively new module that allows you to export and import so-called FNUs. These are a standardized way of exchanging models and simulations for co-simulation, for example. And we implemented support in Chrono for this to both export Chrono models and/or simulations as encapsulated FMU so that they can be used in conjunction with other software, or bring in FMUs that someone else developed and make a more complex system. The MATLAB interoperability, it's relatively simple. It just sends data back and forth to MATLAB. For example, if you want to test some linear solver in MATLAB that we don't have in Chrono, maybe to decide if you want to implement such a solver in Chrono or something like that. And then we have a ROS module. I assume that most of you are familiar with the robot operating system. It's an interface to ROS2 in Chrono, and this allows us to do a lot of the autonomy work that's happening in the lab and be able to connect either different software nodes with ROS2 or replace one of the software nodes with an actual physical system. And finally, as I said, we have these Python and C# wrappers. These are created automatically from the C++ code using Swig. So that's a tool that takes C++ code and wraps it so that it's callable from C# or Python. All right. As I said, we're almost halfway through it, and but I just want to give you an idea of Chrono. So this is how you'd use Chrono. As I said, you don't have a nice GUI to connect things and stuff like that. You just write code. You describe what your system is in code, right? And you call different Chrono C++ functions. In this case, this is for how you would model a slider crank. It's really not much. And then you just simulate the system. In Python, you do the exact same thing. Because not everybody wants to write code, as I said, we provide a bunch of importers from different third-party descriptions and specification, and we create this. For example, this is the URDF description of this RoboSimian JPL robot that you just use the parser on this file and it creates this model. Same for biomechanics, and this is our vehicle specification, which can be done, specified completely to JSON files, and you get a full vehicle model. As I mentioned, we also have an interface to Chrono Unity, so this will hopefully give you a GUI for Chrono. We just replaced the physics-based physics in Unity with Chrono, and you can model things in Unity. Now, this is still a work under progress and is mostly focused on vehicles for now. As I said, I want to go through very quickly now through all these modules of Chrono using vehicle systems as a prototypical multi-physics problem. So especially when you're thinking of off-road vehicles, if you use everything that you can in modeling this, then you end up with problems that will touch upon many modules of Chrono. So you have multi-body dynamics for the vehicle and the suspension and the steering mechanism. You probably want some finite element models of the tires to capture tire deformation. And you can have this going over deformable terrain. So you use either granular terrain of this continuum granular model that I mentioned. And you can think that this all happens while crossing a river. So you have also water interacting with everything, right? So these types of problems you can do with Chrono, but it will involve lots of pieces from Chrono to put this together. Okay, so in terms of rigid and flexible multi-body dynamics, this is the rigid multi-body dynamics is by far the oldest part in Chrono. It's fully mature, and you'll find in Chrono all the capabilities that you can find in a commercial software in terms of bodies and joints and force elements and markers, all sorts of constraints, and actually a little bit beyond what some commercial tools give you. In particular, the way we do frictional contact, we implement two different formulations, which you'll not find in most commercial codes. They usually do only penalty, but we do both penalty and complementarity, and I'll show you in a little bit later, hopefully we get there, what these are about. So these are the equations that you have to solve for rigid multi-body dynamics. I'm pretty sure that you went through this. These are the index 3 DAEs of multi-body dynamics. And this is only the part of a set of equations that will be extended later when we add contact and friction. Finite element support in Chrono, as I said, we're interested in nonlinear finite elements, and more precisely in large displacements and large deformation. And this is because the types of systems that we want to use finite element analysis for are, in the case of vehicle system, prototypical tires, right? So you have obviously large displacements and rotations, as well as large deformations when the tires are underinflated, as you need for deformable terrain and so on. We support a bunch of different formulations, both co-rotational and ANCF, for example, and some other more exotic elements. This can be connected to each other, so you can mix different elements in a single model, and you can also constrain the finite element meshes to other finite element meshes or to rigid bodies, like the tire, right? So the finite element tire needs to be connected to the rigid wheel body. And of course, you can do contact, so interaction with the environment, both mesh to mesh, finite element mesh to finite element mesh, and mesh to rigid solids. I suppose you're gonna cover something of finite element. This is just the type of equations. I just wanted to tell you that this you're solving some PDEs that are discretized to ODEs or DAEs using finite elements, right? So another type of mathematical model. Moving quickly through Chrono vehicle. So Chrono Vehicle does not bring in new physics. It just allows you to leverage and piggyback on things like the multi-body capabilities of Chrono or the finite element capabilities of Chrono, and quickly put together models that represent a particular type of mechanical system, namely ground vehicles, wheeled or tracked. And this leverages the fact that these type of mechanical systems have relatively few topologies. And by topology, I mean, what are the bodies, how are they connected, and how are they working together? And so Chrono Vehicle provides this template approach to modeling and specifying vehicles, in which these templates are templates for each different type of subsystem. So we have templates for different suspension types, templates for different steering mechanism, and so on. And these templates are fully parameterized models. So you can change in a particular template all the masses, inertias, geometric dimensions, specification of force elements, and so on, so that that particular subsystem matches now the one on the vehicle that you want to simulate. There are a bunch of types of vehicles and vehicle subsystems for wheel vehicle and track vehicles. These are all different templates. And of course, in order to have a full simulation, you need subsystems for additional things beyond the multi-body system. You need models for tires, and we have a sequence of different types, models for the terrain, and we have rigid terrains or deformable terrains with different formulations. You need powertrains, which means engine models and torque converters for automatic transmissions and transmission models. And finally, you need a driver model, a controller to specify how the vehicle is controlled at any given time. Something that provides the inputs that go to a vehicle, which are steering input, brake input, throttle input, clutch input if you have a manual transmission, gear, and so on. And then you can run this monolithically or as a co-simulation. But these are the major subsystems that take part in the simulation of a vehicle. And you see there a Humvee, a Chrono Humvee model that undergoes a RMS course, which is a standard mobility test for off-road vehicles. This is an example of a template for a double wishbone suspension. This is a representation of the so this would be the simplified real-world physical model, if you remember back to the first slide, right? This is what you want to simulate with Chrono. Chrono Vehicle abstracts this into this template. And once you specify all the values for masses and inertia of the different bodies and different dimensions here between connections and so on, you have a mathematical model of the double wishbone suspension corresponding to the vehicle that you try to simulate. This is a bit long, but it's a movie. This is the Unity interface. And I think it's... so this is what we have right now in terms of capabilities in model and bringing in Chrono vehicles in Unity, also leveraging what Unity can give you in terms of modeling the environment and so on. And as you can see, you can specify all sorts of things for the vehicle, which you can do through Chrono Vehicle. These are the curves for the engine for this van here. I don't know what else Josh did here. But then you can start simulating it, and you can extract all sorts of information from the simulation. Now, this is really not taking advantage of Unity yet, because Unity gives you very nice graphics. So this is now what you can do when you also bring in some nice graphics. We also have a ability of specifying a path that the vehicle should work. One of these driver models that we have in Chrono implements a lateral controller, which is a path following controller, and a longitudinal, which is like a cruise control. So you set a speed and it will go there. And then you can get this kind of simulation. Of course, you can you can expand the visualization in Unity with all sorts of more interesting information for an engineer. But this is also and this is not necessarily just playing with Unity. This is important, for example, in autonomous vehicles, because you need to exercise somehow your sensor. So, and you better have a good representation of the environment. Otherwise, your sensors will not match, your sensor inputs would not be close enough to the sensor inputs in a real vehicle. So this, I think, goes a little bit longer, but this is the kind of stuff that you can do now. And this is a full chrono vehicle model like the ones that I described before. Okay, let me skip this, oops, in terms, just for the sake of moving forward. Okay, so just very quickly about terrain mechanics. So you saw these vehicles interacting with terrain, right? If you are interested only in vehicles on city environments or on the freeway, that's really not that difficult, right? It's been done for many, many years, right? What's more important is interaction of vehicles with deformable terrain, once for applications in like military applications or in agriculture or in construction. But more recently, and for the last, I don't know, 5-6 years, we've been very heavily involved in simulating extraterrestrial rovers, right? So interaction of moon rovers or Mars rovers with the regolith, which is deformable. Obviously, no freeways on the moon or Mars yet. So I just wanted to tell you a little bit about what capabilities we have in terms of terrain mechanics in Chrono. I am not going to talk much about what you can do with this, except for this slide. So if you do have the capability of modeling deformable terrain, then you can do all sorts of interesting analyses, like looking at the distribution of pressures in the contact patch of tires, or looking at different performance metrics of a vehicle, like the drawbar pull, looking at the relative importance of internal tire pressure and internal stresses in the deformable terrain, or look at the effects of multipass, right? So multipass is important when you have a convoy, because the second vehicle will always evolve in the deformed terrain that was on the ruts that was generated by the first vehicle. But even for a regular vehicle, the rear wheels do not see the same terrain as the front wheels, right? Another thing that you can do if you have this capability is use it to optimize design, right? And this is an example where different types of this were for a rover, the Viper moon rover. We try to see what is the best design of these Grouser wheels. And this was done with a Bayesian inversion, but we simulated and we defined some metrics, how well it climbs, how well it steers. And from those, this ended up being the best wheel design out of 4,000 samples in this space of parameters. So this is what you can do if you have the ability to model deformable terrain. Now, how do you model deformable terrain? Well, arguably the most accurate way of doing it is with this many-body approach, this granular dynamics approach, where you model individual soil particles and the interactions between all these soil particles. And this is the Curiosity Mars rover evolving on granular terrain. The problem with this approach is, even though we have what we claim is a pretty efficient implementation on the GPU of this approach, this takes thousands of times longer than real time. So this real time factor here tells you how many seconds of computer time you need to simulate 1 second of real world, right? So for granular dynamics, this is thousands, right? So if you want to do a simulation, simulate what this rover does for 1 second, you have to wait 1,000 seconds. Okay? Now, more recently, we've been looking a lot at this continuum representation of granular dynamics. This is, if you want, like a homogenization of the granular dynamics equations. and solving an equivalent set of PDEs. So moving to the continuum representation, a set of PDEs that we solve the same way as we do fluid-solid interaction. So at this point, whether this is water and they are and this phase is modeled with the PDEs, the Navier-Stokes PDEs, or if we decide it's soil and it's modeled with these continuous PDEs that model soil, is the same thing. We have the machinery to solve these kind of problems. And we worked quite a bit in the last 6 or 8 months on this. We have simulation that can be as fast as only 10 times slower than real time, with an accuracy that is comparable to granular dynamics. And we validated these two against each other. So this is the method of choice. Now, sometimes you actually want to do this in real time. And for that one, we have another approach, the so-called soil contact model, which is a semi-empirical model of this one. And this can run at real time for relatively simple vehicles. That RTF of 1 means real time. 1 second in the real time can be done in less than a second on the computer. But this one, of course, when you go down, you can only bring down the simulation time by giving something up. And usually you give up some extra physics, the ability of capturing something. So this model, for example, it's fast, but of course is not as accurate as the previous ones. So I have 15 minutes more, and I wanted to go quicker. So I'm going to skip a little bit slides from now on. These go into the details of either formulation or implementation of different modules in Chrono. These are the different ways in which you can do granular dynamics in Chrono, and on the right, some applications. I mentioned. Was that? I thought someone said something. I mentioned that there are 2 ways of doing frictional contact. Chrono supports both of them, both the smooth contact formulation or the non-smooth contact formulation. This is something that few, if any, commercial codes support. Usually they go on this. They have pluses and minuses, and that's why we provide both, because in certain applications, one fits better than the other. I'm going to skip these slides here. As I said, I'll make all these slides available and you can look a little bit more. Remember that early on I had this set of equations in the red thing here, which are the index 3 DAEs for multi-body dynamics. When you want to extend this with frictional contact in a non-smooth formulation, the complementarity formulation, then you have to add some terms in the equation, some Lagrange multipliers, additional Lagrange multipliers with additional conditions. Now this one, as you can see, don't look like the equality conditions that you have for bilateral joints. These are complementarity conditions. And this already makes the problem not be a DAE anymore, but rather a differential variational inequality problem. So you probably heard that DAEs are more difficult to solve than ODEs. Well, DVIs are more difficult to solve than DAEs. So the complexity of the problem increases. And if you add also friction, then as soon as you add something like Coulomb friction, then you actually turn the problem into, you add an optimization problem here, because the principle of maximum dissipation that is equivalent to Coulomb friction introduces an optimization problem here. How you solve this, I'm going to skip for now. When you go here, you'll see this slide that tries to compare the penalty and the complementarity approaches with the pluses and the minuses of each one of them. And if you think a little bit about this one, you can understand in which types of problems one will be better than the other. Let me skip this one. It's interesting, but I don't think I have time. Again, some implementation. This is the fluid-solid interaction module in Chrono. Chrono have different ways of doing FSI. By the way, if you start working with Chrono, you will see that almost everything can be done in at least one way. So it's a quite exhaustive code, and because for certain problems, different approaches work better than the others. The same way as we had these two formulation for frictional contact, we have different ways of doing fluid-solid interaction. The most general one is this partition approach, which is a co-simulation between the fluid and the solid phase. And for the fluid phase, we use so-called SPH, smoothed particle hydrodynamics, which is a meshless method of solving PDEs. And a meshless method is really good for fluids where you can have lots of interparticle displacement, relative displacement. And if you were to use a mesh-based method, then you'll have a lot of distortion of the meshes and problems with that. I'm going to skip that. So this is the smoothed particle hydrodynamics. I do not expect you to understand this unless you work in this one, but the SPH is a way of semi-discretizing some time-dependent space PDEs, like the Navier-Stokes, for example, semi-discretizing in space, right? You can use different ways of replacing the spatial derivatives in such a PDE with algebraic expressions so that you end up with a time-dependent ODE or PDE. SPH is one such method that approximates the continuum field with particles that carry information, and from the information that's carried by each particle, you can always evaluate field values or derivative of the field values at any point, and so you can semi-discretize your PDEs. I'm going to skip this, and of course, then you have a fluid phase, which is done with SPH, and again is done on the GPU because this is a suitable type of problem for GPU computing. It matches well the parallel programming paradigm for GPUs. And then you have the solid phase, which are rigid or flexible bodies done with Chrono, and it's a one big co-simulation then. So the solid moves, the displacement is given to the fluid sees that these solids moved inside, it generates some forces that are applied to the solids again, and it keeps going. And then you can have problems like this. This is some work that we're doing with the National Renewable Energy Lab on these flap devices, which are ways of harvesting energy from waves, right? So this is done in a wave tank here. We just look at, and then validate our simulation, and then we'll design flaps that are then installed in the ocean. And these are some analysis of that simulation. This is the CRM. Again, I'm going to skip that. I already showed you. This is the continuous representation of granular dynamics, which results in a PDE, which we can solve with the SPH method, which we used for water before, but it's yet another time-dependent spatial PDE that can be treated in a similar way. Okay, very quickly in terms of applications, and I'll stop after this, but before I go to the application, I want to mention one thing. The last set of slides in this presentation, which unfortunately I will not get to, are probably the most important ones. And these are about validation. You remember the very first simulation loop that we had there. The loop gets closed through this validation. So you get some results from the simulation, but until and unless you compare the results that you get from simulation with some experimental measurements, all you have is a video game. It's not an engineering tool. You can only use Chrono or anything like Chrono to make predictions with engineering meaning only if the tools are validated. So this is a continuum process for us. Whenever we add something in Chrono, we need to make sure that it predicts reality, in the sense that if we get some results from Chrono, we have some confidence that if we were to do the exact same experiment in the real world, the experimental measurements would be close to what Chrono predicts, right? So validation is critical in simulation. You can generate images like this, which again look okay, but this is not good enough. You need to validate in an objective way and compare simulation results with experimental results. The last set of slides show all sorts of validation studies done with Chrono, and I really encourage you to go through them and see what it takes to build confidence in a simulation software. Okay, so this was just an example of simulating a complex scenario of a vehicle going over deformable terrain, in this case, granular terrain, and hitting some obstacles. This was an interesting project that we had with JPL that was quite a while ago. They were building this RoboSimian robot, and they were playing with different ways of actuating the robot so that it can move. It has wheels, so it can drive. It can just fix the wheels and walk like that, or it can do some weirder motions here in order to advance itself. And they didn't know which one is more energy efficient. So we did simulations, and through simulations, we showed that excuse me, that driving or inchworming are the most effective ones. And this was done by simulating them on granular terrain or on SEM in this case, and capturing all the torques at all the joints and converting this into the energy that is needed to actuate these things. This is a simulation in which this is the Viper moon rover. We are trying to validate our models on granular material, as you can see here, and validate it against some lab experiments in which this rover was climbing a hill. This is actually a hill climbing. The gravity vector here, it's inclined, so that's one way of modeling going up a hill. Another interesting application was, so this is again the Curiosity rover. This is a picture of the wheel of the rover on Mars after a while. As you can see, there was a lot of damage. The reason for this damage is that the Curiosity rover, as deployed, did not have traction control. And when it was climbing hills like this, the wheels were slipping at different rates. Obviously, when you have some wheels on the incline and some wheels on the horizontal terrain, the slip of the wheels is different, and that one was so some wheels were slipping too much, leading to this damage. So we looked at seeing if we can develop a traction controller for this one that controls the slip, depending on what it's doing, and we show that we can do this by also saving energy. So it's more energy efficient and preserves the wheels better. This is not a application, it's just a demonstration of capability. This is a Polaris vehicle going over this RMS course. As I mentioned, RMS courses are a standard mobility test for off-road vehicles. This is a study on CRM of the interplay between internal tire pressure and the stress in the terrain. And the question is, as some of you may know, when people go off-roading, they always deflate the tires. And this is because that is the most efficient way of navigating a deformable terrain area. And you can show this through simulations. These are some examples of fluid solid interaction, both fording with a track vehicle or liquid sloshing here on this wheeled vehicle. This is a more recent example. This is SPH here. Remember that I told you that this multi-particle hydrodynamics model water is done with particles that carry pressure and density and things like this, interacting with a floating wood place and the vehicle going over this. This goes very slow because the video was itself slowed down 10 times to see what's happening. Actually, a simulation on a good GPU runs about at this time. So if you were to run the simulation, this is the runtime visualization based on VSG. So that's what you would see on your computer as the code runs, about this speed for this problem. Okay. 2 more minutes to talk a little bit about support of machine learning and autonomy in Chrono. So there are some modules that I already mentioned, PyChrono, so being able to run Chrono simulation from Python, thus allowing interfacing with machine learning frameworks like TensorFlow or PyTorch or Theano, Caffe, and so on. The Chrono Sensor module, which I realized I don't, well, you can see some examples here. These are outputs from Chrono Sensor. This is a camera here and I believe a LiDAR there. So this module, then the ROS framework in Chrono. Some of you are familiar with GIM. We have a set of environments modeled in Chrono that allow you, like this course here and the city intersection and things like that. And then if you have multiple vehicles and you want to have them all to be autonomous and simulate at the same time, you can use this Synchrono module in Chrono that allows this distributed simulation of agents that I mentioned. And here is an example of reinforcement learning. I'm not going to go in the details of what that means, but what we did, we took a vehicle like this and we trained it to go from one corner to the other corner of this terrain while as fast as possible while avoiding obstacles. And once we did that, in order to test the robustness of the policy that we developed, we ran tests on different types of terrains with different densities of obstacles, and you'll see at some point on snow. And this is an so-called end-to-end approach to autonomy, meaning that the input was just what the camera and the LiDAR, the sensors, see, and the output was directly commands to the vehicle. So we didn't do any perception or planning and control. It's just take the inputs from the sensors, train this neural network that produces controls for the vehicle. What should be the steering input? What should be the throttle and the brake of this Gator vehicle here, John Deere Gator? Okay, I'm gonna skip this one. This is some toying with quantum computing. Another thing that you can do is generate so-called mobility maps, this is the Monterey Bay Area in California, which is color-coded at every single point. So this is probably, I don't know, 20 by 20 kilometers. Every point, the color represents the maximum speed that a vehicle of a certain type, in this case, you'll see a track vehicle, not a Humvee, can achieve at that location given some current conditions like moisture and things like that. And of course, you have to run, especially if you want to get stochastic. So also give a confidence interval to your prediction of the speed that a vehicle can achieve at 10% level, 50 or 90%. You have to run Monte Carlo simulations. So at each point in this 20 kilometers by 20 kilometers, you have to run like 10,000 simulations. So here are millions, hundreds of millions of simulations here. Obviously, you cannot do this with full simulation. So you construct reduced order models, either through machine learning or dynamic kriging, which is what we did here. And you use Monte Carlo on this simplified thing. And then you can come up with these maps. These were maps in terms of slope, soil, and saturation, so a measure of moisture in the soil for a particular track vehicles with different levels of confidence. Okay, I'm not. Before validation, the last thing here is about co-simulation. In order to accelerate these multi-physics things, you simulate all the parts separately. We talked briefly about co-simulation during this hour. So I'm going to stop right here. And this is the one section that I said it's very important, but I will not have time to cover.
Very good.
Okay,
Very
but
good. So
I'll stop here and maybe take a couple of questions. I don't want to just disappear.
very good. Okay, guys. So this is your pretty much once in a lifetime opportunity to ask a question from the guy that knows computational dynamics back and forth. So you heard it all the stories about quantum computing and GPUs and so on and so forth. So if anything in your mind, anything from the examples you saw just a few minutes back, please unmute yourself and shoot it.
So it's not the last time that you're going to see me because I'm going to be in La Granta in 3 weeks and I'll have the door open to anyone who wants to talk about Chrono or anything that I talked today.
That is correct too, but that's going to be the week that most of the students are already off. So that's an exam week, so they may not be here.
Got you.
But anyway, so but also you need to know this. We don't communicate in Finland, so I'm going to be very surprised if there's any comments, any questions. But we'll see. We'll see. We'll see. You actually, it's something that I got interesting in the beginning because you said that the Chrono is almost like a 30 years old code. Because if I remember correctly, it was initiated from Italy, and then
So Chrono started as Alessandro's thesis code, but it was very limited. It was the core multibody stuff, which itself changed quite a bit in the meantime. Everything else came after that, and So I think in the last 12 years, probably most of Chrono, almost everything that you saw here, except multibody dynamics, came in the last 12 years or so.
It may be hard to evaluate, but any estimate like how many companies are using the Chrono at the moment?
It is very difficult to estimate because of the type of license that we have. So they don't have to tell us. So we discover more and more companies that use it. We know of at least 2 companies that use this and embed it with some nice graphics and other GUI and all that and sell it as such. But for example, the US Army uses it. This is Chrono it's Chrono Vehicle in particular. So Chrono Vehicle, this ability of modeling and simulating ground vehicles was funded by the US Army and is used as their vehicle dynamics code.
Okay.
But then in wind energy, there are a lot of companies out there that use this. Total Energies, for example, Goldwing in China, a bunch of others in China use Chrono to model wind turbines.
And then it's quite interesting that there's one company that is currently building the new factory to Lappeenranta, and they are using the Chrono. And that company is Danfoss. So they use
Danfoss uses it. Yes. There are quite a few. As I said, we cannot really keep track of that unless they tell us. But it's also used quite a bit in national labs, in academia, quite a bit. So many groups use it for granular dynamics, like in nuclear energy, right? For nuclear reactors. to model the pebbles that are there. So the granular dynamics, the stuff of Chrono. As I said, wind energy now, this project that is ongoing and I'm part of with the National Renewable Energy Lab, we want to create this entire suite of tools for simulating wave energy devices. It's all based on the Chrono framework. So.
Okay. All right. So let me take a look. So no one is unmuting.
Oh, and I should not forget, NASA is using it quite a bit for simulating extraterrestrial rovers. And hopefully in a couple of weeks, I'll start a project with the European Spatial Agency for similar things. So,
very good.
Okay,
Very
I'll
good.
stop here.
Okay. Hey, so guys,
There's a couple of questions in the chat window. Have a look at that.
in the chat.
Yeah. Can you look at them? Because I don't know exactly how to do that while keeping.
Yeah. Okay, I see. Yeah, I can read it. Thanks, guys. I did not notice that. So the first question is that have you worked with the simulating hypersonic cases such as rocket engines or combustion events?
No, so we don't do anything in the air, and because that's we cannot do everything, and aerodynamics is a field by itself, and there are very mature codes that can do that. So we work on improving the way of co-simulating with third-party solvers, and so this is how we would get there. Now, because we don't do aerodynamics, we also did not look in rocket engines and things like that, which it's another thermodynamics and things like that. We did very little on that kind of application. So no.
Right, and then there is another question which is goes like this: has Chrono or any maritime simulation possibilities?
I'm sorry, what?
Maritime, so something like waves, and I think that's the case.
Oh,
because
yeah.
we saw this example.
Yes.
Yeah.
So that's precisely one of my main focuses these days is improving the fluid-solid interaction thing. So we're looking at wave energy devices, and then we're going to look at tidal energy devices, and eventually we want to look at underwater robots and ships maybe, but we don't really have we didn't hear of interest in that area, but we're certainly working in this direction. Eventually, we want to get to autonomous underwater robots, because that's also of interest to NREL.
Okay. Good thing. All right. So I was about to say that what follows is that there's going to be a hybrid lecture, business as usual, next week, Monday, getting started at 4:15. So I hope to see some of the guys in person in the lecture room. And those of you that I cannot make it in person, you can see me in YouTube channel. And I'm gonna upload all this material that been recorded in this week and the previous weeks to the YouTube, so you can prepare yourself to the midterm exam that is coming soon. All right, I want to thank Radu. Thank you very much.
And just one last thing. So I understand that people may not be around when I'm in La Peranta, but I'll send these slides, and on the last slide you have my contact information. Just feel free to email if you're interested in any of this stuff. I'll be more than happy to answer.
Fantastic, really good. Appreciate that. Okay, so that's it. So can we give a big hand to Radu? No, you don't do it like this. You do it.
Thank you, guys. No need for that.
This way.
Look, I got the.
Yeah.
Thank you all.
Nice.
Good luck in the exams.
Okay. Thank you, Radu, and this is it. So we're gonna close the meeting and gonna see you next week, Monday, in business as usual. Take it easy, guys. See you soon.
Bye.
Bye.